Okay, thank you everyone for coming to this last session of the day. Thank you for staying. Already last 5 minutes because of, display. Anyway, so what I told, just if you want to know about me, just read that slide, but I lost 5 minutes, so let's go right to the topic today. So we're going to talk about what you've listened for these 2 days, which is performance, and performance. So how to optimize performance. And in general, it's been what I've been doing for the past year at Gradle, so optimizing everything with the rest of the performance team, of course. So the agenda today is to talk about different concepts that made it possible to have such a big performance improvement in Gradle for last year. So incremental builds, the concept of compile avoidance, incremental compilation, and some variant-aware dependency management if I have time. Luckily, it's the last slot of the day. You're not gone yet, so I'm going to talk for 1 hour and a half and hope that you're not going to miss your plane. Okay, so let's talk about incremental builds, which is the very first concept that you need to understand about Gradle. So last week, actually, I started, about that blog post about the release of Gradle 4.0, and we gave those numbers, Maven versus Gradle, and friends of mine actually didn't believe me, so they wanted to try it by themselves, and one of them is a famous committer in an Apache project that I won't name, but he's using Maven, so he wanted to try Gradle, and he tried that, and he was saying, okay, actually, Gradle is not faster for my use case. I said, why? It's because I'm running the tests, and the second time I'm running the tests, actually Gradle is up to date. It doesn't run the tests. So I need to clean and force Gradle to run the test again. Say, okay, so this is, that kind of psychology that you have to switch when you move to Gradle. Because Maven, basically you have to test everything every time, but you have to do clean every time. And this is a loss of time. And I had to explain to him that if he has to run the tests every time, then something is wrong, either with the tests or with the build. But in any case, if you have tested once, it should be okay if the sources have not changed. If you have to run the test multiple times, then either it means that your tests are flaky, which in this case means you have a bug to fix, or it's a problem with the build because you maybe execute a test in parallel and they interact with each other. So maybe you have to create some splits, whatever. So fix that. And so doing clean basically is a waste of time. And as explained in the keynote and various talks here, time is money. Money is important. And if we can get money back, that's cool. So the very first thing that you have to do is just that simple incremental test. So you run Maven test, it runs the test again, but if it does that with Gradle, then something is wrong. So if you run the same task again, do not change. If it executes a single task, you have a problem and you need to fix that. Okay, so how do I properly write my tasks to be incremental? And what does it mean to be incremental in the Gradle world? So Gradle has that concept of inputs and outputs. And this is really like in the functional world, a function is a task. A task is a function. It is exactly the same. So same inputs, same outputs. So we will take a fictional example, a task that would build a shaded jar. So for those of you who are familiar with the shadow plugin, this is something that already exists, but imagine it doesn't. We want to build something like that. So a shaded jar is basically a jar that is more or less like an Uber jar, so something that bundles all your dependency into a single jar, but it also remaps some classes from a package to another. So this is how you would configure that task. You create a shaded jar, it has a jar file, a class path, and a mapping. And you, as the developer of that task, you know precisely what are the inputs and outputs of that task, right? You know that jar file is actually an output, and you know that class path and mapping are inputs of that task. So if you, as a developer, as a build author, as a plugin developer, you know that this is an input, you know that this is an output, then you should tell Gradle, this is an output, this is an input. Because if you don't, your task is not incremental. So it's going to re-execute every time. So how do you do that? It's actually very easy. So you just create a task in whatever language you prefer. So in this case, it's just plain Java, and you have to annotate with that simple annotation at input files that just declares to Gradle, hey, this property is an input to my task. So class path is a file collection, and that file collection can contain dependencies, can contain regular files. It doesn't matter. All that Gradle cares about is that it is an input. Similarly, for my mapping, I have to declare that this is an input to my task. So by doing that, what I do is just, if a file in that collection changes, or is removed, or added, then Gradle is going to understand that the task is out of date, so it's going to re-execute it the next time. If the mapping changes, same. But we still miss one piece. And the piece that we're missing is pretty obvious. We didn't declare the output of the task. So similarly, just create get jar file, which was corresponding to my jar file property in the configuration block, output file, and then there you go. You have declared precisely those are my inputs, those are my outputs. So in this case, it's done in a class file, which declares a task of type shaded jar. But you have to know that if you want to do it in line, and you will have to do it in line, so you have probably some tasks which are declared directly in your build script, you also have some methods to declare the inputs and outputs. So just be aware that you don't have to create a specific class file to do it. It is better to do it because you can test your task type. You can potentially make it a plugin, publish it, etc. So in the end, it's going to become a proper task. But to prototype, it's often easier to have it directly in the build file. OK, so once we've done that, input, outputs, nothing more to do. Everything is either up to date or out of date. And by just doing that, if you use the build scans, obviously, you will get that information when you run a build. You will know exactly what changed. So Gradle knows, and it will tell you. So in this case, I'm executing a build, shaded jar, and it will tell me, OK, this task has been re-executed because the value of the property mapping has changed. And this is super important. So you give to Gradle all the knowledge that you, as the developer of that task, you know about. So you know about it, tell it. So this is really the simplest thing that you can do about tasks. But actually, this is not as smart as we can be. Because what we say is, here are my inputs, and here is the output of the task. But the outputs, well, if you remove the file, you have to re-execute everything. But if an input changes, maybe you can be much smarter. What if actually in the whole set of inputs, only a single property changed, and in that property, only a single file changed? Well, you can declare a task that will have that information. And that's what we call the incremental task inputs. So we come from a global input to something which is much finer grained. So we know exactly what changed. So we can imagine that task and declare something like that. So instead of having a task action that just works with the whole set of inputs and every time works with the whole set of inputs and re-executes everything, you can ask Gradle, OK, please give me the incremental task inputs of this. And then, okay, there are two possibilities. Either this task is executed maybe for the first time, or a clean before, and then you don't have any input, any output available, so it's not incremental, I have to do everything. Or it's incremental, and then you have methods that will let you work on each of the inputs and process as you need. So it means that you, as a designer of a custom task, you can implement incremental logic. And we encourage you to do it, of course, because you can potentially imagine that if the mapping here didn't change, and the only thing that changed was just adding a class on the class path, then you don't want to reprocess the whole set of classes because potentially it's super expensive to do it. You just want to process the new class which has been added or modified. And if it's deleted, just only delete the output. So do the minimal amount of work, and then again, well, time is money, so super important to do that. But I would say that what is important to recognize is that you have the choice. So you can start with a simple task that doesn't work with incremental inputs, make it work, and once it works, you can optimize it to be even more incremental and work on specific inputs and outputs. So Gradle will tell you this file has been added, deleted, etc., etc. Okay, so now the next concept I want to introduce to you is what we called compile avoidance or compilation avoidance, whatever you want to call it. And this is really one of the biggest issues that, well, most of other build tools users have. So, and before Gradle 3.4, you had the problem too. Maybe you didn't recognize it, but you have it. So this is basically compile class path leakage, and I'm going to explain what it means. So this is a typical dependency graph that you would have. And this is often what I present to people who tell me, okay, why do you don't have just a single JSON file with your dependencies, and I don't care if it's a compile, test, runtime, whatever dependency. I would just want to declare the dependencies. Actually, we have different types of dependencies, and it's super important to make the difference between the different types of dependencies that we have. So a typical dependency graph, A depends on B and C depends on F and G, etc., etc., etc. So this is a dependency graph between modules. I don't care if it's an external dependency or not. It's just a dependency graph, right? So what it means to recompile something which is at the bottom. But basically, it means that you have to recompile everything up to the root. So this one changes, so I need to recompile H, I need to recompile E, B, A, etc., etc. So recompile everything cascading. So this is terrible for performance, because what I change is something which is just at the root, a leaf actually, and then everything goes up to the root, just because this is a dependency that almost everyone depends on. But what does it mean here to depend on that library? Do we actually care if it changed? We don't know at this point, right? So it is even worse than that. And when we call dependency leakage, this is probably the worst problem that you're going to face, and that you probably faced and that we face as Gradle developers too for plugin authors. So when you declare something in compile scope, what does it mean? It means that the dependency that you put in a compile scope is also transitively available to the consumers of the library. So say I'm depending on Guava, and I say compile Guava, and then someone depends on my module, then transitively it gets Guava. But does it mean that he needed Guava in the beginning? Probably not, but now in the IDE it's available. So it's super easy actually to start using Guava just because it was transitively available. And then you leaked something which was an internal detail into the public API. And then if you decide as a designer of a library to change and remove Guava to use just Java 8 collections because they're faster, because they use the lambdas, etc., then you cannot, because consumers of your library depend on Guava. So this is the worst situation that you want to avoid in the future. Avoid leaking dependencies. And to do that, we introduce the separation of API and implementation. So the example is exactly this one. I have a class with a method, and that method is just get names on a set of person. So person is something that is provided by my module. It is a model. And then internally, I'm using Guava. Immutable set, copy of, etc., etc. I don't care, right? I could use something else. I could use Java 8. This is my internal usage. It doesn't leak into my API. Here, I'm not using Guava. So before Gradle 3.4, this is what you declared. You said, OK, as a consumer, I depend on the project model, and I expose Guava. I need Guava. The problem is that this person class is something that leaks into your API, because you need that in the method signature. But this Guava is purely internal, and compile doesn't let you make the difference between the two. So starting from Gradle 3.4, what we started to do is to introduce a new plugin, which is called the Java library. And this one models the fact that a library exposes an API and an implementation. And the two are separate. So my API exposes the model, but it should not expose Guava to the consumers at compile time. It only cares about that at runtime. Runtime, Guava is going to be needed, right? But at compile time, Guava should not leak to the consumers. So what does it mean in terms of dependency graph? It means that we have two categories of edges now. In blue, you have API dependencies, and in gray, it's just implementation dependencies. So now what happens if I'm changing something at the bottom? The difference now is that only H is recompiled. It only recompiles the direct consumers of my library. So H needed I as an implementation dependency, so it has to be recompiled if the bottom changes, because potentially we broke internal APIs. But as soon as H is compiled, it doesn't have to recompile everything else, just because we don't leak that dependency transitively. So we just interrupted the whole recompilation chains very early. So you can imagine that for a bigger project with tons of submodules, maybe 100, maybe 1,000 submodules, as we can see in the wild, it matters. And it matters also because you don't leak the dependencies anymore. So it is also a maintenance problem that you're just going to solve there. OK. So now, if I change an API dependency, so say I'm going to change H, then clearly I need to recompile E, B, and A, just because those were API dependencies. So H was a dependent of E, so I need to recompile it. But then B needed E, so I need to recompile B. And then A dependent on B, so I need to recompile. So you just go up to the top, right? So it's nice, but we can do better. So how we can do that better is that we need to make the difference between the different kinds of consumers of a library. So separating the API and implementation is nice, but there is something else that we need to think about. What is the compile class path? What does the compiler, the JavaC compiler, need to compile something? What does the compiler care about? It has an input. The input is jars or class directories. these are the libraries that you are using, right? Your dependencies. And it has the source files, of course. A jar is just a set of class files, and the class file contains both the API and the implementation. So for those of you who are familiar with the native world, C, C++, etc., you know that in this world, you cleanly separate the API implementation. You have the .h file and .c or C++ file for the implementation, but the headers are just the API of the component. In Java, we don't have that separation. The file contains both the API and the implementation, which causes all the troubles that we've seen. So let's fix that. What we provide to the compiler today is this. We provide the full implementation of the class. We tell it, here's foo, and here is all the internal data is. But actually, what the compiler cares about is just that. It only needs the name of the class and all its public members. It needs the signatures of the different methods. It needs the types, it needs the public constants, etc., but nothing more. It doesn't care about the internal implementation of the methods. So if it doesn't care, we shouldn't. But even more, if you change the order of the methods in your source code, should the compiler care about that? Shouldn't. I mean, it's just something for cosmetics. The API, what you compile against, hasn't changed. So we shouldn't care about that. Only the public signatures matter. So what Gradle does now is compile class path snapshotting. And it works like that. So I take a jar. Well, I have a class. And I'm going to compute a signature for that class. And then all the classes of the jar are going to produce a signature for that specific jar. And then we compute all the jars on class path. It computes a signature of that. And then, well, the result is my compile class path hash. But that only cares about the public members. So what the hash consists of is only what is relevant to the Java C compiler. So we have a hash, and this is only what the compiler needs to know. And in particular, if you change an implementation detail, you add a comment in your source file, you change the order of the methods, you change the body of the methods, you change local variable names, the compiler should not care about that. It doesn't have to. So the signature is going to be exactly the same. On the other hand, once we run the application, then we have a different class path. We have the runtime class path. And what does the runtime care about? The runtime cares about everything. It needs to know about everything. It needs to know about the classes and the order, not the order, the value of the constants, the method bodies, etc., etc. And it has to know about the resources potentially on the class path. So runtime needs to know everything. So we have to compute a different signature. So in practice, how it works is that we annotated our compile task with two different annotations. One is @compile class path that basically says this is a compile class path, so you can ignore properties file we change in the jar. The compiler won't care. It won't even try to load them. It doesn't matter. And the other one is just @class path, which means should be actually named @runtime class path, which means this is useful for runtime. So if you change something, some implementation detail, then only consumers that care about the runtime should change. So we have made the difference between the compile and runtime class path, and they have different semantics, right? It's not just about the values that you put on the class path. You can have compile and runtime class paths having exactly the same jars. The semantics are different. One is used to compile, the other is used to run. And Gradle makes the difference. So in the end, what we make is to ignore all the irrelevant ABI, non-ABI changes to the compile class path. So it seems like magic, but it's not. It's really trying to do something smart. So the effect is that when we change H and we recompile E because we have to check if actually we change the public signature, so maybe we broke something, once E is compiled, we're done. Because we didn't change anything in E. So it's just compiling again against my library, and if it passes compilation, done. We know that we didn't break its API. And you have that for free. You don't have to enable it. It's already in Gradle 3.4, so we just interrupted the whole cascading chain of recompiles for free. So it's pretty cool. But actually, it's even smarter than that. It means that we don't care about the names of the jars. So if you have a class path with a library and you move from 101 to 102, it's actually following the semantic versioning scheme. So we upgrade the dependency. What changes is only an internal detail. The signature is going to be the same, and you want to recompile. It's pretty cool, I think, at least. Okay, so next. So we talked about incremental builds, being smarter than compile avoidance, but then we have the notion of incremental compilation, which is some kind of incremental task inputs that we do for free for you. So the idea is that you have this whole set of source files that you want to compile, but we're not going to recompile everything. We're only going to recompile what is strictly required. So this is language specific because Java and Scala and Kotlin don't have exactly the same semantics. They don't need the same kind of inputs. So it is very specific to a language to know what you need to recompile when you change the source file. But to enable that feature, potentially we're going to enable it by default in future versions of Gradle. You need to opt in today unless you're using Android, where for Android it's enabled by default, you didn't even notice. So enable it, but what it means in practice is that you have a library which uses common math, and inside you're just using the complex class and complex.i, right? So complex is a dependency of my library, and it means that if complex is changed, then I need to recompile library because I need to check if I broke something. Right. But if a different class from complex, from the jar, is changed, if I don't use it, why would I recompile my component? We don't need to. We only need to recompile classes which are affected by the potential changes of a single class in the jar. So that's what the incremental compiler does. But there are some gotchas. So imagine that we have that. A library utils that uses the DFP class, and it has a constant there. So DFP is a dependency. We change the max x value in DFP somehow, and then because it's a dependency, well, we should recompile. Okay. You like that, right? This is bytecode. Yeah, I know. Friday afternoon, last session, I want to show you bytecode. I think it's cool. So if you dump the bytecode of that class, you would see that actually there's no reference to DFP because the Java compiler is allowed to inline variables. It is able to inline constants. So the value of DFP of something was inlined directly in the bytecode. So when we analyze that, we don't know that there was a dependency on DFP. It has gone. It has disappeared from the class file. So there are some tricks to improve that, but basically we cannot rely on just the Java language specification. It doesn't say that when inline something, it has to add something in the class to tell, okay, this was inline from that class. So we know that the Java 8 compiler does it. It introduces a reference in the class constant pool to say that, but it's not standard. So we cannot rely on that information. So just to summarize, what we do is just we analyze all the bytecode of all the classes. We record which constants are used in which files, And when a producer changes, we just check if a constant of that file has changed. If it is the case, then we need to fully recompile everything because we don't have the information who was the user of that specific constant. So yeah, just have to, it could be surprising because you could say, okay, only a constant change, so why do I need to recompile everything? Who uses annotation processes? Okay, so you're suffering. If you use Lombok, please use something else because it is really terrible for performance. Use auto-value, it's much faster. So if you use annotation processes, just know that it disables incremental compilation. So we are working actually with the Google and Groupon team to propose an API to fix that. So annotation processes authors will be able to declare that their annotation processes are compatible with incremental compilation. So it's going to be fixed, but not today. Something important is that an annotation process is not something like a jar on your class path, right? Its implementation matters because it is used by the compiler. So you cannot just snapshot an annotation processor jar like you snapshot a jar on the class path because its runtime matters because runtime is actually compile time. It's not too hard. Runtime is actually compile time. Okay, so that's the runtime of annotation processes. So what it means that you should never add processors to the compile class path because if we detect that you do that, we have to disable all the incremental compilation goodness. So instead, you need to use the new annotation processor path variable and declare a configuration, say, okay, I'm going to use apt. Yeah, I think it's dead. Better? Sorry for my voice. It's because of allergy, so I'm going to be dead. Oh, hey, I don't have battery. So that's how the talk is going to end, with me dying and no battery. Full stop. So configurations apt, we just declare a configuration and then declare that dagger actually is in the apt configuration and then compile only dagger. So the compiler is something that needs to be in an annotation path and the runtime on compile only. And when we do that, actually, yeah, incremental compilation works. So in Gradle in the future, we're going to provide a default configuration to declare your annotation processes. Just be aware that today, this configuration is not enabled by default, so you have to create yourself. Okay, so I have around 5 minutes to finish with variant-aware dependency management. So this is a word that you've probably heard multiple times this week, and I want to try to explain to you why it is super important. The reason it is super important is that we make the difference between the producers and the consumers of a library. So a consumer depends on a producer, but in the end, there are multiple requirements, different usages. And when I explained the difference between compile class path and runtime class path, there was actually a difference for different usages of the same library. Different context, one for compiling, the other for executing. So what do I need to compile against a producer is something. What do I need to run with a producer? What kind of artifacts does the producer offer? So typically in the Java world, it's super simple because we bundle everything in a single jar. And well, there was that promise that you can take any jar and run it anywhere. I'm not sure it's true, but yeah, it was a promise. And then in the end, we don't care if a producer is external or internal. What we care about is to choose the right version of the producer for the right use case. So imagine that you are in the native world. You don't want to compile a dependency with a 32-bit format with a transitive dependency, which is ARM. typically. It wouldn't make sense to link that way. So you need to be aware of the different kind of dependencies that you have. So what does it mean in practice? So when I compile against a component, I need the class files. I can find them in different forms, class, jars, AARs. And the question that the consumer is going to ask is different depending what he wants to do. So the question is, do I need the jar to compile against the component? Is it really a jar that I need to provide to a compiler for it to work and compile against me? Maybe, maybe not. So we have the notion of usage, and we're going to say, okay, please, producer, give me something that I can use to compile. And the producer is going to say, hey, sure, I have something. Here's a jar. And effectively, you can take the jar, compile against it, and it works. But the jar is only one variant, one solution that the producer gives you. But maybe it can be smarter. It can tell, hey, actually I have a class directory. Maybe it's fine, you know? You don't need to process the resources. So only the class directory should be enough for you to compile against me. And maybe it's going to say, I'm sorry, I don't have a class directory, I don't have a jar, but I have an AAR. But actually, I know how to transform an AAR into something that you can use to compile against me. I know that I can unzip, and in the unzip, there's going to be a class directory. I'm going to provide it to you. Don't care. So 3 variants, class directory, jar, AAR. And actually, not all those variants are equal. To build each of them, you have different dependencies, different task dependencies. So one is probably cheaper than the other. So what it means is that if you apply the Java library plugin today, it first is going to try to use the class directory because it's the cheapest. Just compile the classes, done. If it cannot produce a class directory, maybe it's going to provide a jar because it's an external dependency and all you have from Maven repository central, it's just a jar. So yeah, it's fine. But what it means in practice is that if you use the Java library plugin, if you compile against a project, when it's going to give you the classes, it's only going to trigger the classes task and not the jar one, because jar is only required at runtime. And you might think, okay, he's saying, I don't need the jar, but I know that in practice I'm going to need it because I'm going to run the test in the end, so it's going to need the jar. Well, not necessarily. It can provide the class directory and resources directory. But more than that, it means that we can defer the execution of the jar to later. So I can parallelize much better what's going to happen. Instead of just building a jar and then providing it to the consumer, I can just build the classes, start running my tests, and then only sometime in the future going to package it into a jar. And it can happen in parallel. And that's a huge benefit. So in conclusion, why does it matter? Because of this. So this is the graph that you can find in the blog post that we wrote a few months ago when the 3.4 release of Gradle was out, and we explained that notion of compile avoidance, etc., etc. So, well, if you use Maven today, you're doomed, so forget about it. But if you use Gradle, please at least upgrade to the 3.4 version. That's a minimal, because you would benefit from compile avoidance for free, even without changing to the library plugin. Okay? But then, if you change your application to use the Java library plugin and enable incremental compilation, then this is the kind of numbers that you're going to get. It is way faster. And really, this is without the build cache. So imagine if you add the build cache on top of that. So yeah, just incrementalness is not just words. It is something that you should care about, just because it matters. I mean, well, unless you want to have coffee, and yeah, maybe I'm just ruining your life at enterprise, well, whatever. So yeah, this is all I have to do to complete this talk today. Just 5 minutes for questions before I leave you, and yeah, whatever. Sure. Yeah.
I have a question with the compiled avoidance.
Yeah.
When you do a non-API breaking change, what happens with the test? You rerun the test?
Yes, because of that. So the question is, if I do a non-API change, are the tests re-executed if I change something? And yeah, yes, because we make the difference between compile class pass and runtime class pass. So you're going to run test, and then we're going to see, oh, for compile we don't need to recompile, but then when we reach the test class, then the hash of the runtime class pass has changed, so we need to re-execute the test. So yeah, it's smart enough to do that. Yes?
You say that Gradle calculates hashes for all classes on all libraries in the class path.
Yes.
Will it not create another performance problem when there are too many classes on the class path?
The question is the fact that we snapshot all the classes and compute a hash, is it a performance impact if there are many classes? Well, actually no, because it was already the case before. So when we computed the hash of all the inputs to make sure that it's up to date, there was always that hash being computed. It's just the hash itself which is different. So it has a little of a head because we need to analyze the class file, extract the ABI, etc. But in the end, the performance impact is huge, so it's totally invisible for you. And in the end, we don't recompute the same hash twice for the same jar. So it's cached, etc., etc. So yeah. Another question? Yeah.
Yeah, what about alternate JVM languages? I'm particularly thinking of Groovy, static compile, and Kotlin. And what are their strengths and limitations at this point?
Yeah, so it is language dependent. So this is for Java. For Groovy and for Kotlin, Kotlin has an incremental compiler so it's not using our infrastructure to do it, but they do it. For Groovy, there's not. So it means that it's using the whole class path hash. And there are reasons for that. So because, yeah, mostly because of AST transformations in Groovy. So they can be on the same class path. So it is more complicated than just extracting the ABI.
What about the other optimizations?
So compile avoidance, yeah, it should work just because for external dependencies, well, actually it shouldn't matter. But otherwise, well, what else? What other optimization do you have in mind?
Your whole presentation is just...
We don't have an incremental compiler for Groovy, so yeah, no. Yes?
First of all, I can add to the first question that like everything works for Kotlin, like avoidance.
So no, it's the same. So for Kotlin, they have their own incremental compiler. So no, because they have to explicitly opt into that compile class path stuff.
Anyways, I have another question. So in the example of the shadow jar plugin,
Yeah.
one of the inputs was mapping.
Yeah.
And in the implementation, we used like is incremental.
Yeah.
What will happen if mapping if we'll change mapping? Will it be still incremental?
Yes, it's going to be incremental. Yeah, it's going to be incremental. Yeah. What you have with incremental task inputs is the files, basically, so you know which are added, removed, etc. So you can still check in the mapping if something has changed. Yes.
So the code library that I work in is about 100 different sub-projects that apply the Java plugin.
Yeah.
And I think a lot of dependencies have been declared by people who didn't really know the difference between compile and runtime, such as myself at the start of this presentation. Do you have any advice on how to transition to use of
Yes.
library?
That's a very good question in terms of, yeah, I should probably have said that. So if you migrate from the Java plugin to the Java library plugin, what I recommend is to use implementation instead of compile. So you start with implementation, you build, it will blow up, but that's okay. It's just that everything that blows up means that it leaks into your public API. So you have to review each dependency. So it's going to say, okay, this dependency is missing, this class is missing. So was it really something that I intended to expose or not? If it was intended, that switched from implementation to API. And if it wasn't, fix it.
Thanks.
Yeah, so that's all for today. Thank you for coming again. Thanks for attending the conference and happy to talk with you after. So, thank you.